Okay, so I guess we'll start. So my name is Ajmain Yamin. So today we're going to talk about a project we did in last summer at the topology geometry workshop with Moyer Cass, and it's called map coloring on surfaces. So first we need to talk about what are surfaces, right? So a surface is just a space where locally it looks two-dimensional. So for example, a surface could be the surface that is a sphere. So this is a surface. Another example of a surface is the surface of a donut. So this is a torus. So, and another example of a surface is a surface is like a three-hole donut. So, okay, so these are all surfaces, and so for each surface, we have a number that's sort of counting the number of holes in the surface. So here, you would say it has one hole, right? So that's the donut hole. So here, the genus is 1. Whereas here, it has no such holes like this, so we say the genus is 0. And here, the genus is 3. So for each non-negative integer, we have a surface which will denote sigma g, or maybe we write sg. And this is notation for the surface of genus G. Now we can start talking about maps.
So a map is a decomposition of a surface into faces or regions on this map that are homeomorphic to density. This means that if I cut them out and I bend them around a little bit and wiggle them around, they'll look just like a density. These are examples of maps on various surfaces, and you can see they consist of these different colored regions, and each of them is some single blob like this in some form. There are no things where you have like a washer and you're missing things in the center, or there are no everything can be bent around so it looks like a regular old disc. These divisions are made up by a graph consisting of vertices or points on the surface and edges between them. And together these bound out the regions on the map.
So why don't we give an example? So the simplest, a very simple example of a map is this map on the sphere. So this map on the sphere has 4 regions, and it might be easier to understand it as a tetrahedron. Right? So the tetrahedron has 4 faces, and then each face becomes one region. So this map on the sphere has 4 colors. So we're considering maps which are complete and maximally.
So a map is complete if any 2 faces on the map are adjacent. That is, they share a portion of their boundary, like this. They share an edge on their boundary. So if these are 2 faces in the map, face 1 and face 2, they're adjacent because they share an edge. It's not sufficient for them to be adjacent to only share a vertex. So suppose this were region 3, this would not be adjacent to region 2. So if any pair of faces in the map, the faces are adjacent, then your map is complete. So on any surface, there's a maximum number of regions in a complete map that depends on the genus of that surface. And a map that is complete and has this maximum number of regions for the surface that it's on is said to be maximally complete. The number of faces in a maximally complete map on a given surface depends on the genus according to this formula. This number is called the Heawood number and has a long history related to the 4-color problem.
So why don't I do some examples of this? So here, I'll erase some of this. So we have the genus, and the Hewitt number. So in genus 0, if you plug in 0 to that formula, you'll get 4. So what that's saying is that on the surface of genus 0, the sphere, the maximum number of colors you can achieve such that each two colors are adjacent to each other is 4. And that's this tetrahedron. This is a maximally complete map on the sphere because it has 4 regions, and each region is adjacent to each other. And the Hewitt number says that the maximum number of regions allowed is 4. For genus 1, we have, plugging 1 into that formula, we get 7. So what the Hewitt conjecture is saying is that on the torus, the maximum number of regions you can have such that each region is adjacent to every other region is 7. And here is the 7-color map on the torus. Okay, so you understand why the tetrahedron is a complete map, because you can see that every 2 faces are adjacent. How can we understand that this is a complete map? So one interesting thing about this is that it consists of 7 hexagons, and they're arranged in this circular pattern. And then you just have to look at one hexagon and verify that it touches every other hexagon to prove that it's a complete map. Because by the symmetry, every other hexagon has the same local 7. So here, let's focus on this, let's say, gray hexagon. We see it touches pink, purple, or pink, dark purple, light purple, and green along this corner, along this part. So that's already 4 regions. And then we follow along the strip and moving all the way along, and then come up out here, and then we get yellow, orange, and the green was already counted before. So you get 2 more regions. So that says that this gray hexagon has 6 surrounding neighbors. So it touches all 6 other regions in this map. So this gray hexagon is adjacent to every other hexagon, and that proves that this is a complete map. And by the Hewitt formula, you know that it's a maximally complete map. Oh, I think we already explained this. Okay.
So here are some more examples of maps on the sphere, which are all complete, but none is maximally complete.
The one on the
Yeah,
very
that
right
was,
is maximally.
right.
Could you explain why that square is a...
Sure, sure. So here, you have a square with its sides identified as follows. You have an arrow here, and here like this, and another one here, and here like this. And if you draw this diagonal, and you fold up this square like a taco, so that these arrows align, they fold together, and these arrows here fold together. And imagine you had paste along the edges of the square here, right? So that these stuck together when you folded them up. The figure that you get would be, in a sense of how you could deform it, a sphere. It folds up like this and gives a sphere. Anyway, these are some partitions of the sphere into regions that are colored. Here you have 2 regions, 3 regions, 3 regions, and 4 regions. And these you can verify in these that all regions are adjacent each to each other.
Okay, here's the maximum complete map on the torus again. And this is how you can represent the torus as a hexagon. So we have planar diagrams for each of our maps. So it's hard to work with 3D shapes. So we're going to represent them in these polygons with their edges identified. So here you have a hexagon with opposite sides identified, and then this sequence of moves shows you how it's actually a torus. So now we have some base maps on the torus. So the left one is a hexagon. If you look at it here, you see that it has 3 pairs of opposite sides that are distinct colors. So here it's purple, here it's purple. So these 2 sides are identified, and then these 2 are identified, and then these 2 are identified. So it's actually a hexagon, even though it has a lot more vertices than a hexagon should have. But since we glue them like this, then they fold up like this, and then we get a torus. Okay? And then this has 7 colors, and then it also, when you fold it up, you can check that all of the regions touch each other. So this diagram is a way to represent this physical model. Right? Now here in the middle, we have another torus, where instead of a hexagon, we're going to start with a square, and then identify opposite sides. Right? And here, so we're identifying opposite sides, and then we get a torus like that. Imagine you take a square, and then identify opposite sides to get a 2, and then identify the boundary circles to get a torus. So here, this map has 6 colors, whereas this has 7 colors, and this also has 6 colors, but this one is using the hexagon instead of the square.
So what is tuples?
What? Oh, these tuples? So we're going to denote a complete map of genus G and C colors by the tuple GC. So this is 1, 7, because it's genus 1 and 7 colors. And this is 1, 6, because it's genus 1 and 6 colors. And these are the corresponding tuples for these.
So here you have an 8-color maximally complete map on genus 2 torus shown here. And what we've done is we've cut it and unfolded it like a hot dog bun. You put a plane right through here and you just peel it open. That's how it looks. And these would be the identifications you would need to make to get back to this surface here.
Yeah. So like the hot dog, the vertical, the hot dog strip, the long edge of the strip is like this vertical line. And then you're folding along this vertical line so that this edge gets identified with this edge gets identified with this edge gets identified with this edge, and this edge gets identified with this edge. So you fold it up, and these inner circles get identified with each other. So that's how you get the genus 2. Right? And then this has 8 colors. And also, for the Hewitt number here, if you plug in 2 into that formula, you'll get 8. So this is a maximally complete map on the genus 2 surface. So why are we talking about these maps on small genus with varying numbers of colors? So the objective was to construct maximally complete maps on surfaces of genus, at least construct the maximally complete map on the genus 3 surface. So we know by the Hewitt conjecture that, or theorem, that the complete map on the genus 3 surface has 9 regions. Right? So we should be able to find a map on the genus 3 surface with 9 regions. So at the start of our project in the summer, we didn't have such a map. Right? Well, we knew they existed because the Hewitt conjecture says so. Right? But we don't have a good picture for these maps. So we wanted to construct them in a way that's understandable. You can actually construct them by taking a bunch of, octagons, and then gluing octagons along the edges, right? So you have a bunch of octagons, so it looks like a flower, right? And then each of these octagons have edges which get identified to each other, and then you fold it up, and each octagon is a different color, right? And then you fold it up in such a way that you actually do get a genus 3 surface, and then by construction, every region is touching every other region. So now you have 9 colors, and it's maximally complete on the genus 3 surface. But the problem with this, and this is actually, this was in a paper, and they presented this setup. Instead of drawing the octagon, they had a matrix with all of the, well, yeah, you can just give this setup as a matrix, actually. But the point is that when Connor was trying to represent this physically, it was very complicated, and it wasn't turning out right. You want to talk about it?
Right. You have to draw a 56 guy on Microsoft Paint. That's not even started. You draw a 56 guy on Microsoft Paint and partition it into regions. And then you have to cut off little itty bitty sections of this 56 guy and paste them, rotate them, and paste them in other places, and redraw the whole figure, and do this about 300 times. And in each stage, what you do is you reduce the number of edges of the polygon. You have to make it a little more complicated, and then you reduce the number of edges. And along the way, the division into regions gets more and more complicated. You're transferring the complication of these various edges into the interior of the map. And when you're done with it, you get something that you can fold up. But now the regions are long, narrow strips that go all over the place. You know, they have all sorts of bifurcations, and they're hideous. You can't understand it. So we were lucky to be able to find a different method of constructing these maps that gave maps that were much easier to understand, and we can explain to you now.
So, should I explain this? So here's this is not the very first construction that we found. Connor found the first one, but it wasn't this one. This is the second one, and it's based off Connor's idea. So when Connor presented the first solution, that got me excited, and then I came up with this one, which is based on it and a little bit different. So the idea is to start with 2 complete maps on surfaces of lower genus. So by the way, this figure that I'm showing you here is a representation of a maximally complete map on the genus 3 surface with 9 colors. So what does it mean? First you take 2 surfaces of lower genus. Right? Here's the genus 1. And then we take a genus 2, or no, genus 0. In other words, this is a torus and this is a sphere. And then we have 2 colors on this map, and we have 7 colors on this map. So in total, we have 9 colors. And we want to connect them together so that we have a genus 3 surface with 9 colors. So how are we going to do that? We're going to make some punctures, right? I'm going to make a hole here, and a hole here. And I'm going to make 3 holes here. Okay? And then I'm going to associate this hole with this hole, this hole with this hole, and this hole with this hole. So the numbering is given on the screen over there. And then what I'm going to do is I'm going to take a cylinder.
Do I use like colored chalk for this?
Oh, right. Yeah. Thank you for suggesting that. Yeah. I guess the main thing is to have these 2 colors, pink and yellow. So pink and yellow, or brown. Let's see.
Yellow's
That is brown, actually.
oh,
So pink and brown, and then
Wait,
along.
no, those look the same.
What?
They look the same.
Really?
Okay, fine. Fine,
they
whatever.
look less different than pink and yellow.
Yeah.
Do you want to use pink and yellow?
continue. It's fine.
Okay.
Like,
So along this side, so what we're going to do is we're going to take a cylinder and then attach one end to this surface and the other end to this surface. Along this side, we have a pink edge. So really, we're going to extend this pink along the cylinder, and then half of the cylinder will be pink. All right, you have to imagine this. Okay, so half of the cylinder, let's say the lower half of the cylinder is going to be pink, and it's going to come and attach here. And then the other half is going to be brown, and it's going to be on the top. So pink and brown. Okay. Here's pink, and here's all right. So, and now we're going to come along here and then attach this end of the tube over here. So, an easy way to see how we're going to attach it is we're just going to label around here the sides that's pink and the side that's brown. So here, I'm going to have a pink that comes down here, and a brown that comes down here. Right? So that's the first tube. And it's kind of hard to see on this diagram, but that's exactly what is around this boundary circle over here. And then for each of the two other circles, we're going to do the same thing. This pink is going to come along and then attach maybe over here. This brown is going to be here. This brown is here. And then this pink is going to be here. And this brown is going to be here. Now let's just check which colors the brown touches. From this boundary circle, it touches these two. And from this one, it touches these three. And from this one, it touches these two. And then the pink touches these three from this circle, these two from this circle, and these two from this circle. So we started with 2 complete maps. Here, there were 7 regions, and every color touched every color among these 7 regions. And here, we had a complete map of 2 colors, and each color touched each other. And then we connected 3 tubes between them. Let's see. Like this. Trying. Like this, 3 tubes. And then we saw that the pink touched every color here, and the brown touched every color here. So now we achieved all of the connections. Every color here touches every color here. So now we have a complete map of 9 colors, and the genus of this map is going to be, so the genus of this map, there's an easy way to see what it should be. We have a torus here, and we have a sphere here, and then we're attaching 3 tubes. So it's easy to see what the genus is. It's 1, 2, 3. So now we have a complete map on the genus 3 surface with 9 colors. And that's basically the idea at the heart of all of these constructions. You start with complete maps on a small genus, and then connect them with these connecting tubes.
So Moira, who's the advisor of the math club, she crochets objects, all sorts of mathematical objects, and like to crochet these for us. This is the map that is shown here in the diagram, this 9-color map on the genus 3. And here you can see the component that came from the 7-color map on the torus, and the component that came from the 2-color map on the sphere. Here's the little sphere with 2 colors, and these are the 3 tubes joining them together. So I'll pass this around if you want to look at it and verify with some effort and time that all of the regions indeed touch all of the other regions. go through that?
Yeah, why don't you?
Okay. So here,
Wait, was this the first one that you came up with?
no,
Okay, this is the
second.
second.
Okay. So here, we're going to construct a 12-color maximally complete map on genus 70. And we're going to do it by connecting two 6-color complete maps on torus. So, base maps here are 6-color maps on the torus. There's six regions here, 1, 2, 3, 4, 5, 6. And these two sides are identified straight off. And then the top and the bottom are identified with a slight shift, so that this top part here comes out down here, so that region 3 touches region 4 and region 5. And then, here you have extending this is where this pops out down here. And here you have region 1 and region 2. So this is a six-color map on the genus 1 that is complete. We take two of these, and we remove from each of them 6 disks. Let's give these colors. So we'll have so here we have green, we have pink, we have orange, no, this is brown, so we'll call it brown. We have a blue, we have a purple, and we don't have an orange, so we'll use,
You want orange, I want.
we have an orange. Here we have orange. Likewise, we have orange, purple, pink, and orange, pink, and green. We're going to remove a disk at each of these valence 4 vertices. Here you have another vertex that's coming off the side of the map. And then we're going to remove 3 more disks down here. Sorry. One between region 1 and region 6, one between region 3 and region 5, and then one over here between region 2 and region 4. And then over here, we're going to remove disks again at each of the valence 4 vertices. And then in the center of each of these edges here, between the top and bottom, regions. And we're going to connect them in the same way via these tubes. Let me see one of these for a model. Brown, blue, green. So we're going to take this disk here, the boundary of this disk, and identify it with the boundary of this disk here, so that the pink region is now adjacent to regions 2, 3, and 5 on this map. The brown region is now adjacent to regions 3, 5, and 6. And here we go. The green is adjacent to region 5, and the blue is adjacent to region 3. And then we're going to look at the next valence 4 vertex. This one over, this disk here, between green, blue, orange, and purple. And then we're going to we're going to identify it to this valence 4 vertex here, so that green touches 6, 3, and 1, and brown below it, who already touched 6 and 3, touches 6 and 3 touches 1, 4, and no, I'm sorry, these are faces. This one just touches 1. So now on these two vertices, or these two identifications, the green and brown regions have both touched regions 5, 6, 3, and 1. And we're going to put this with the other side. We're going to set orange down here like this. Green, brown. No. Put orange down here. And then purple coming up like this. And doing this, when we add the next one, each of these top-bottom pairs will have touched the same 4 regions on this map. And they'll each have 2 regions left to touch. And we'll solve that by taking a disk out between them and setting it down on the edge between the 2 regions they have both yet to touch. Right? So for instance, if we consider green and brown again, they both touch 5, 6, 3, and 1, and they're both missing 2 and 4. So here, we consider this disk between green and brown. We remove it, and we set it down between 2 and 4.
So
Oh, that's this one, yeah, like this, 2 and 4. And now they've touched everything. We've left ourselves room to repeat this procedure for the remaining 2 pairs. And that's how we establish all the connections between the regions on this map and the regions on this map. So the genus 7 is in the process of being crocheted. This has been a very long process because here you can see a map on the genus 6 and already how convoluted this is. Right? This is pretty hard to understand. If you had to do this the original way, where you were cutting it out on Microsoft Paint, it would be ungodly. But the genus 7 is a little more complicated than this. So even though it was one of the first ones we found, it's not finished yet, the model.
Okay. So now I want to quickly talk about the genus 6 because it's my favorite one. It's my favorite one. So it's very symmetrical in the sense that, okay, so when you have a map with, when you're trying to form the connect sum of a genus G with C colors and a genus G prime with C prime colors, and you're connecting with n removed disks from each of them, you're going to get a map with the total genus is going to be G plus 1 minus n. Is that correct?
Yeah.
Or n minus 1?
Right.
Okay. Right. So, for example, if G was 1 and G prime was 0 and n was 3, then you're going to get the connect sum is going to be 3. So that's how we took what?
G prime
Yeah, G prime.
down
No.
here.
Okay, yeah. Thank you. So, okay, so that's how we took a torus and a sphere connected with 3 tubes to get a genus 3 surface. So, in general, it works like this. And then what we want to do is form the connect everything here with everything here. So we'll get C plus C prime colors. Right? Okay, so on this surface, we already have how many? We already have the total number of connections, and here we have its total number of connections, but we want to connect C colors with C prime colors. So we need C times C prime connections. So we need to make C times C prime connections. If we started with the genus 1 with 6 colors, genus 1 with 6 colors, and another genus 1 with 6 colors, then we're going to end up with a genus, and then we make, what is it, 5 punctures? Right? Then we're going to have this much. And the number of colors is going to be 12. So we get, what is it? 6. 6. So we get a genus 6 surface with 12 colors. But what we need to do is make 6 times 6 connections. So we need 36 connections. And the point is, here, around each vertex, so this is, we're using this base map, the one on the right. So it's kind of like this. So we have 6 pentagons meeting at a single point, and then we're going to take advantage of this single point right here to make a puncture here. So we get a circle with all 6 regions on its edge, on its boundary. And then we're going to do this twice, so we're not going to just have one of these, but we're going to have 2. So let me draw that quickly. Something like that. And then we're going to attach this circle to that circle with one tube that goes all the way around. But this tube is going to come out with 6 colors on top, on it. So this tube is going to have 6 colors, and it's going to land on these 6 colors in a way that you get 12 connections from there. So this, for example, this color right here, or let me put it here, this color right here is going to touch this color over here. Or I might have done it the other way on the board. But what we're going to do is we're going to take each segment here and then shift it just a little bit so that it touches 2 segments here. So then, yeah?
You have hexagons over here, right?
Yeah.
You have pentagons over there.
Yeah. What?
See different. Are they different things?
What do you mean?
Those are the pentagons meeting at one point, aren't they?
They're pentagons reading at one point, but then we got rid of this vertex, right?
Yeah, this is a mistake. In that this really should be a single edge on all of these. These should have flat edges where they extend out. When they're repeated, the center does look like this. You can think of these as pentagons, continuing on to the center.
Yeah, but the point is that this planar diagram is not complete in the sense that if I made a puncture over here, you have to repeat the puncture down over here as well, but we haven't shown that.
Right.
Like, you have to imagine that it's still over here, so then here there's still pentagons. Okay, so in this way, we get 12 connections because each hexagon here touches 2 hexagons here. There's 6 hexagons, 6 times 2 is 12. So we got 12 out of these 6, right? We got 12, but how many more do we need? What? 24. We need 24 more connections. So how are we going to get 24 connections, right? So 24 is just 6 times 4, right? Okay. 6 times 4. So we're going to take 4 more tubes, and each of them is going to afford us 6 connections. So those are the 4 tubes, and they're drawn like this. So we have 1 tube here, 1 tube here, another one here. Wait, no, 1 here. And the last one here. And then the same, so what's so nice about this is that it's kind of symmetrical because the same kind of thing is going on in both base maps. Right? So what you're going to do is you're going to have these four punctures, and then you're going to identify them in pairs like this. So these two get identified, and these two get identified. So you have these pair of tubes, and then they come out like this. And then these two also get identified, but you're going to take this one and identify it to this one, and then this one to identify this one. So they kind of swap places as you go from here to here. So this is 5 and 4, and this is 4 and 5. Right. And then what you can argue is that around each of these circles, you have three regions, right? 1, 2, 3. And over here, you also have 3 regions. And by the same shifting a little bit argument, you get 6 connections from each. So each of these circles gives you 6 connections, and you have to check that they're distinct connections. And this is the hard part. Like, actually, once you think of this idea using this base map and then using this 6 color boundary circle, then all you have to do is find 4 more things, and you just try a little bit, and within like 30 minutes you can find you get this. But this is the very last map that we found, and the hardest part was coming up with this original idea to take this base map, right? This one on the right. So this was what we always worked with, but now if we shrink this middle region down to a point, we get a new valence 6 vertex. And we can abuse this valence 6 vertex to get 12 connections right off the bat. So that's the part that was really great about this. And this is the last map that we found, and it's actually this one.
So what's also so special about this map is that all of the regions are adjacent. Each region is adjacent to each other region, but is adjacent to each other region through exactly one edge. That is, the map is non-redundant. There are no 2 edges that have the same face on both sides. And any map can be made so that that's true. But what's special is that this simultaneously satisfies that at every vertex there are exactly 3 edges coming together. So you can make it, that's called trivalence. You can always make a map trivalent, or you can always make a map non-redundant. But this is only satisfied simultaneously in a maximally complete map for special genuses. And this is exactly when the Hewitt number is given by this formula. This occurs exactly when this interior part of the floor function is already an integer. And this and the floor function is doing nothing. And that's what's happening here on the genus 6, and what happens on the genus 1 and the genus 0.
Over 2. This should be 12, right?
Should be 12.
Exactly 12, right? There's a radical there, but it's still exactly 12.
Yes.
Okay. Yeah.
So that brings up another thing. So we started with complete maps on the torus and on the sphere that are very symmetric. They're symmetric in the sense that if you consider any region in either of these maps, it's indistinguishable from each of the other regions in the map. Right? You can do some rotation, and the one is mapped to the other, and everything's preserved. But when we were coming up with these maps on the higher genus surfaces, they were much less symmetric. Even on the genus 2, this has some symmetries, but you can tell some regions apart. This has a top-bottom symmetry, in a sense. But on the higher genuses, these symmetries aren't there.
So the reason we wanted to find symmetries is because they help us verify that the map is complete. And this is good for presentations because, like, when I started the presentation, I verified this was complete by just looking at one face, right? So that's the advantage to having regular maps, meaning you can just look at one face and check that it touches every other face, and then from that conclude that the whole map is complete. But if you don't have a regular map, you have to go through, like we did, and go through every region and then check that it touches every region. So we wanted to find regular maps. So so once we found these examples of maximally complete maps, we wanted to see if there were regular maps. And then what we eventually encountered is that it's impossible. So the only regular maximally complete maps are the sphere and the torus. And this is, I would say, our main result? Right. So do you want to talk about
Yeah, sure. So first we want to formalize this notion of nice symmetry. What do we mean when we say that this map here and this other map here are nicely symmetric? And we formalize this via this notion of regularity. Regularity says that if I consider a vertex edge face tree, so what is that? I have some face, I have some edge that's incident with that face, and I have some vertex incident with the edge and the face. Right? I can map this to any other vertex edge face triple on the map and extend this to an incidence preserving map of the whole map to itself. So an automorphism of a map is a permutation of each of the sets of vertices, edges, and faces in the map. It sends a vertex to a vertex, an edge to an edge, face to face, bijected, and it preserves incidence, so that if two faces were adjacent before you apply the automorphism, they're still adjacent once you apply the automorphism. And they're adjacent via the images of the edges that were adjacent through the beginning.
So another way to think about a regular map is that it's maximally symmetric. Like every symmetry you could have of this map exists as a symmetry, right? So there's symmetry of taking this yellow region and moving it to this green region by taking this vertex to that vertex, and then these three edges, these three faces around it to those three faces around it. And that is a proper symmetry of the map on this torus. So every symmetry that could exist does exist on the map. So that's what regular means.
So on an orientable surface, this means that if you take a single face of the map and you consider a rotation around the center of this face, a rotation of its edges by a single edge, this extends in an incidence-preserving way to a map of the entire map. And the same thing goes around a vertex. If I take the edges incident with a vertex and I rotate them one to the next around this vertex, this extends to an incidence-preserving map of the entire map. And we're going to use this in the proof of this theorem.
So what we're saying is that you can look at a single vertex on this torus with 7 colors, and then rotate this face to that face, that face to that face, that face to that face, and this edge to that edge, that edge to that edge, and that edge to that edge, and do a rotation by 360 divided by 3 degrees. Yeah. And that will be a proper symmetry of this torus, because like the torus is represented by this, and we're just rotating it. So every hexagon goes to another hexagon, so that's fine, right? Okay, and so what it means to be regular is that around every vertex you have this symmetry, and also around every face you have the symmetry that moves this face around.
Okay, so the theorem is that the only regular maximally complete maps are on the sphere and the torus. So in order to prove this, we first prove 2 lemmas, which are that maximally complete maps, regular maximally complete maps, must be non-redundant, must be trivalent. So that is, at every vertex, exactly 3 edges are coming together, and that no 2 faces are incident via 2 distinct edges. They're not adjacent via 2 distinct edges. They're adjacent via exactly 1 edge. So we suppose that we're on a surface of genus greater than 1. That is, we're on an oriented surface that isn't the sphere or the torus. And by Hewitt's formula, we can conclude then that the number of regions in a maximally complete map of this surface has to be greater than or equal to 8. So in particular, we get a configuration of regions in any maximally complete map on this surface that looks like this. You have some region C. You have some region C, and you have a region A, B, and a region D. So here we have a maximally complete map with 8 or more regions. We say consider some region, call it C. It's adjacent with at least 4 other regions, because there are at least 8 regions in the map, and C is adjacent to each other region in the map. So you have a configuration around C of 4 regions like this. And at each vertex, you have exactly 3 edges meeting. So you have a configuration like this in your map, right? Supposing that you have a maximally complete map, a maximally complete regular map that's on a surface of genus greater than 1. And what we do is we say, well, we know we're in a complete map, so this region B is incident with this region D via some edge. Okay. So it occurs, so you have a bunch of more edges here, and then here it's adjacent to region B. Some other things happen. But we can apply an automorphism of the map that rotates the edges incident with face B around B, and takes this region D, rotates it to this part here, where B is adjacent to region A. And we look at what this rotation does elsewhere on the map. In particular, what does it do to this kind of bifurcated form of edges right here, with region D here? Well, it sends it to another one, coming off somewhere around from region B. And now the edge, the face that appears here is the image of D under the same automorphism, which is A. So we conclude that somewhere coming off B, there's a prong like this, and here there's region A. Now we say, well, if we rotate around B by a single step of edges counterclockwise, we send face A to face C. Single counterclockwise rotation around B. And we say, well, what does that do over here? This gives us another prong like this, and A must be mapped to region C. So we have this configuration. Okay. Finally, we say, well, now consider region A. If we rotate a single step clockwise around region A, we send region B to region C. Right? Likewise, if we see what this does over here, let me give myself a little more room to work. Consider this prong of edges coming off A. Right? Here's region B. The same clockwise rotation around A, sending B to C, sends this prong here, it sends B to another prong like this. This was C, and this was also C. Right? This is the image of B under this rotation. So here we have some region, we don't know what it is, call it E, right? But what do we know about it? Well, let me redraw this a little bit so that's clear. One of two things. Either it's incident with C via 2 distinct edges, or these are really one and the same edge. But if this is the case, then E has at most 1, 2, 3, 4, 5 edges, which means that there are at most 6, no, that should be 6. 2, 3, 4, 5, 6. Yeah, sorry, I didn't count this. 1, 2, 3, 4, 5, 6 edges, which means that there are at most 7 regions in that. But we're assuming there are 8 or more. Yeah. This contradicts the lemma we proved that there are no redundant edges in the map, right? Because that says that E has to be adjacent to C via 2 distinct edges. And that's where the proof goes, or we reach our contradiction, and we get that you couldn't have a maximally complete regular map with more than 8 regions, or more than 7 regions. And that's the proof. So, thank you.
Anyone have any questions?
So, yeah. So you said that there was a paper that made research that they use polygonals, right? Isn't that a regular map?
No.
Why?
It's not a regular map because, okay, so we actually asked this question, and it's not a regular map because, first of all, given any map on a surface, okay, given the torus, you can unfold this map to another surface that's simply connected, meaning it has no holes. Right? So like this has a hole here, but you can unfold this to actually the plane, right, which has no holes, by just tiling it with those squares where we said opposite sides are identified. Right? So yeah, this is the plane which we were using here, right, or here, right? When we said like this hole has to be repeated down here because it's periodic. So yeah. Anyway, if you have a map, you can unfold it. So for the maximum complete map, 7 regions on the torus, you can unfold it to this hexagon tiling of the plane, right? And then, if you had a map of higher genus, if you had a double torus, and this had 8 regions, when you unfold it, you're not going to have a simple plain hexagon tiling, but you're going to have a heptagon tiling. 7 dots. 1, 2, 3, 4, 5, 6, 7. Right? And then you have to tile all of space with septagons. Right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, it gets really hard. But you have to keep doing this, right? And then you keep doing this, keep going all the way around. And eventually, what you're going to get is something that looks like it gets smaller and smaller. So you have to distort the image so that the hexagons get smaller and smaller. So basically what I'm trying to say is that you can reason that it's not a regular map by looking at this picture and then saying this is 1, 2, 3, 4, 5, 6, 7, 8. Right? And then extending these colors along over here. So maybe this is 5 and this is 7 and 9. But you can extend all of these numbers throughout the whole plane. And then you you want to show that it's not regular by doing some manipulations, like rotating along here sends 2 to 3. But then out here, it sends 2 to 4. So it's not an automorphism of the map.
So what property of tiling is that it's happening for 6 but not happening for 7?
It's exactly this argument here. That's what it is. It's just this is a way where you can see. This gives you a way to see clearly what the rotations are doing that you might not see on a folded up surface.
Yeah, that's fine. So the point is, like, if it were a true automorphism of the map, then when I do this rotation here, every instance of 2 in this infinite plane should actually go to the same other region. But when I actually do it for this particular map on the 2 torus, you'll see that 2 goes to 3 here, but 2 goes to 4 out here. So then it's not regular. It's not a true automorphism. Any other questions? Yeah.
So, like, for example, for 12, you could take like squares, right?
12 what?
Like, so you had like, okay, so you want 12 colors, right?
Yeah.
And then you took like 2, 1, 6, 1, 6, right?
Yeah.
So you have the specific formula for this. So I'm just saying, like, why wouldn't you take a different base pattern to get like this maximum?
Well, you could.
Oh.
We thought originally that there's some combination. I mean, certainly, if you don't, if you have things like, I don't have enough colors on these 2 base maps to give me the number of colors I need. Or there's some obvious constraints on what base maps you can use. But we thought originally that there were some pairs of base maps that looked at first, that you could connect them, that you could do a combinatorial argument and say, well, the maximum number of connections we could get for a number of tubes is this many, depending on the vertices, the height, the valence on this one and on this one. But we really need this many connections, and we need more than we can possibly get.
I
In fact, we haven't found a case like this. We thought we found a case like this. We haven't found one. There may be some like this. But we were picking more or less what seemed convenient for us to use.
All right, there, any last questions? All right, well,
Thank you.
talk again.